Okay, so if you're looking for answers for this homework, you're probably going to be disappointed. What I would like to do is go over how you solve these problems and maybe get you started on the implicit derivation. But after that, you're going to have to be able to plug these things in on your own so that you can do the math to help you solve the actual equation. Okay, so it's early in the morning and I'm kind of sleepy. So let's see how we do. Okay, Superman is in a level flight 6 miles above the ground. Okay, so we need to draw a picture for this. Almost all the time we're going to draw a picture to begin with. We've got him, here's the ground, right, is 6 miles above the ground, and I guess he's probably flying in this direction. Let's say, over and past the school, so the school is down here. How fast is he flying? How fast is he flying? So that's this direction, right? So we're going to call this the x direction because that's horizontal. So we were asked for dx dt, the change in his position, right? So this is the derivative of his horizontal position. When the school is exactly 10 miles, so that's this distance, right? This distance is 10 miles exactly from where he is. And this distance is changing at, we'll call this c for the hypotenuse, when this distance is changing at 40 miles an hour. Okay, so we know some things here, and because it's a right triangle, we're going to set up a Pythagorean theorem relationship. X squared plus 6 squared equals c squared, right? Remember, these things are changing. Your horizontal is changing, so it gets a variable, and your distance away from the school is changing, so it gets a variable also. Okay, notice the 6 is not changing. It's a constant, right, level flight 6 miles above the school or above the ground. So when we implicitly differentiate this with respect to time, 2x dx dt plus 0 equals 2c dc dt, right? The change in the hypotenuse. Okay, so let's see. What do we know? What do we want to find, right? We want to find dx dt, which is this. Okay, so we need to figure out all the things that we do know. We know that c is 10. We know that dc dt is 40. We know we can solve for x, right? We have a Pythagorean theorem relationship here where we have 6 squared plus x squared equals 10 squared. So we can figure out what x is also. And in fact, because it's a Pythagorean triple, that's going to be 8. And now we have ourselves a really easy equation, hopefully an easy algebraic equation to solve in order to know what the change in speed, right, his speed is, his change in the horizontal direction. Okay. This is another similar problem where we have that same kind of triangle being drawn. Okay, tightrope at 3 feet per second. So that's going to be this distance, right? Direction is 3 feet per second. At an altitude of 100 feet, so that's going to be constant there all the time. And let's see, the change in the angle of elevation. So that's this here. We're looking for the change in the angle of elevation. Okay, and of course, well, hopefully, maybe not of course, but as your person walks to the left, the angle is going to get less and less steep as he gets farther and farther away. So we should be expecting a negative answer for our angle because it's getting smaller. So we want to know d theta dt, right? What is d theta dt when the walker is 200 feet horizontally? So we'll call that x because it's horizontal. 200 and dx dt, the change to the left position, is 3 feet. Okay, so because he's going left, that's going to be a negative. So we're moving to the left. Right, left is a negative direction. Okay, so once again we have this Pythagorean theorem, right? So we were changing, this is changing, and our angle is changing. No, this is not a Pythagorean theorem. We have an angle. So we need to think about our trig relationships. The 100 is the opposite side, and x is the adjacent side. So it looks like we're going to have a tangent relationship. So the tan is the opposite side, which is 100, over the adjacent side, x, which is changing. The distance the guy is away from the light is changing. Okay, so now we're going to implicitly differentiate this. So maybe you don't know, maybe you do, but the derivative of tan is secant squared. Okay, so that's the derivative of the tangent. Now we have to take our d theta dt, right, the chain rule. Every variable needs a rate. So this is 100, right? It's not actually. Let's get rid of that. This is 100 times 1 over x. Okay, split this into two parts. So we have our coefficient, and then the derivative of 1 over x is negative 1 over x squared. Okay, there's a couple ways that you can figure that out also. And of course, dx dt. So let's see, what do we need to know? We know that x is 100. Right, so we know x is 200. So we'll plug a 200 in there. dx dt is 3. So we'll plug 3 in there. Now the secant part, in order for us to figure out what this whole entire thing is, we're going to need to find our hypotenuse, right? Because the secant from pre-cal is the hypotenuse over your adjacent side. Hypotenuse over adjacent. So if we do our Pythagorean theorem and do 200 squared plus 100 squared, that's something like the square root of 500 is going to be the length of our hypotenuse. Okay, so the secant, we can replace the secant value, this whole entire value of secant with root 500 over 200, and then I'm going to square that. So in squaring 500 over 200, right, we kind of, we lose the square root here, so there's no more square root. Root 500 squared is just 500, but the 200 goes on the bottom. Okay, so when we substitute our 200 in here and our 3 in there, now we're going to multiply by the reciprocal in order to take it to the other side. So we're going to multiply by 200 squared over 500. Okay, and now with a little bit of simplifying, you can get the correct answer. Okay, so we had to find the value of the secant using our right triangle over there. That's probably the hardest part about this problem. All right, let's see what else we got. A lighthouse is on an island 4 miles, so that's a constant 4 miles. And let's see, the beam rotating clockwise, so it's coming this way, right, from right to left clockwise. What is the angular velocity? So angular velocity is the rate of change, right, the rate of change, that's velocity. The derivative of position is velocity. So rate of velocity of your angle. So in other words, this is just d theta dt. Okay, so your angular velocity is the rate of the change of the angle. Okay, and let's see. What is this? 2 miles per minute. I guess that's coming this direction, yes? Coming across a beam of light. So here's our light. It's coming across the beach at 2 miles per second. Once again, this is x, your horizontal distance. So they're telling us that dx dt is equal to 2. dx dt is 2. So let's see, what do we have? When the beam is 1 mile away, so when x equals 1. Once again, this is an angle, and I have the opposite side and the adjacent side, so I have another tangent relationship. So this is x over 4. Okay, so I have a tangent trig relationship here, so now I have to take the derivative of this tangent function, which is secant squared d theta dt equals 1 over 4, right? So we're going to split this into 1/4 times x, 1/4 times dx dt. Okay, so we're trying to figure out what d theta dt is, so we know these certain things, right? We know dx dt from our problem, that's 2 is dx dt, so that can go there. probably a -2 since it's moving to the left, don't worry. And then the secant, remember we have to use our trig to find the secant. So that means if this is 4 and this is 1, this is the square root of 17 is the length of our hypotenuse. So the secant of the angle is root 17 over 4. Okay, so that's going to go in here, root 17 over 4, and then we're going to square it. And then you're going to multiply by its reciprocal, so that will come over here as a 16 over 17. Okay, so now it's just a matter of simplifying, and you've got your rate of the angular velocity. Okay, so a lot of these trig ones, you need to make your Pythagorean theorem, or I mean your trig ratio. You need to make your trig ratio in order to substitute that secant or that tangent or that cosine value into your problem. Okay, so this is also another one where we have this angle that's rotating. Okay, basically the same picture, but now we know that it rotates really, really fast, right? A constant rate of 100 revolutions per minute. So d theta dt, right? If the lighthouse rotates clockwise, so that's the change in our angle, 10 revolutions per minute, and 1 revolution is 2 pi. Okay, so our angle is changing at 20 pi revolutions per minute. Okay, so the clock is rotating, our angle is changing like that. So we're still 4 miles away, and we're still coming across at 2. So dx dt is still 2. Okay, so a very similar type of a question. Only difference is now we have the change in angle, and we're looking for how fast is a beam of light? Oh, we're looking for dx dt. We don't know dx dt, but we know x is 2. Okay, so once again, it's a tangent. Tangent of the angle is equal to x over 4. So our derivative becomes secant squared, because tangent is always secant squared, d theta dt equals 1 over 4 dx dt. So once again, we do that same type of thing, and we use our ratio in order to find, in this case, 4 squared plus 2 squared, that's root 20, right? 16 plus 4 is 20, so the hypotenuse is root 20. Your secant in this case will be root 20 over 4. That we're going to square. Okay, and then we have our 20 pi, which is our d theta dt. And we can multiply both sides by 4 and do some simplifying, and that will tell us what our dx dt is. Okay, so hopefully you're getting the point of this. This is right, the trig ones, right? Whenever we're talking about an angle, you're going to have some type of a trig relationship. Okay, and if you have the opposite and the hypotenuse, well, that's a sine one, and if you have the adjacent and the hypotenuse, that's a cosine, and if you have opposite and adjacent, that's a tangent. Okay, 14 down here. Let's see what we got here. A spherical soap bubble. So how fast is the radius changing? So we want dr dt is what when the volume, when you blow air into it at a rate, so that's the volume is changing at 10 cubic centimeters, and the radius is 2. Okay, so here we have to know our volume of a sphere. So volume of a sphere is 4/3 pi r cubed. That's the volume of a sphere formula. So let's take the derivative with respect to time, dv dt equals, multiply this by 3, and I get 4 pi r to the second power times dr dt. Okay, so we know what the volume is. We can substitute that one. We know what the radius is. We can substitute that one. So then we have to divide by all this stuff, and that will tell us the rate at which the radius is increasing. Okay, so not too bad, I don't think. Let's see what the second page says. Okay, what do we got here? We have a cylinder being drained. So now it's losing volume. So now our dr dt is, or volume is going to be negative. Okay, so that's the key here, is knowing that your volume is now negative. So how fast does the water level drop? The water level is the height. So we're talking about dh dt, the change in level of the height when the radius is 6 and it's being drained at a rate, so the volume is losing at -3. So -3 feet per minute because it's losing height. Okay, so here's our cylinder with a radius of 6. So the volume of our cylinder is pi times the radius squared times h, because the radius doesn't change, right? No matter what the height is, the radius is always going to be 6. Okay, so our volume is 36 pi times h. So taking the derivative with respect to time, dv dt equals 36 pi dh dt. Okay, so simply plugging in our -3 here and then dividing by 36 pi will give us our rate of change of the height. All right, back to some more angles it looks like. Angle of elevation, so that's this one. Let's see, the balloon is rising, so that means our angle is increasing, right? The balloon is rising, so this is the y distance. There's a change in y. They are 500 feet, right? 500 feet from the base of the balloon, from below the balloon. At the moment, the angle is pi over 4, so that's our angle. The angle is increasing, so that's d theta dt. How fast is the balloon rising? So we're looking for dy dt. So we have an angle and we have two sides. So once again, this is a tangent because it's the opposite side over the adjacent side. Opposite over adjacent. Okay, so back to one of these. The derivative of tangent is secant squared. Okay, times d theta dt equals 1 over 500, right? That's our constant, times dy dt. Okay, so once again, we're going to use our trig, right, to find the secant value. We know, oh, do we need to know the secant? The angle is changing up, so the 0.14 goes here. No, the angle is pi over 4, so this is going to be a unit circle one. So we're going to find the secant at pi over 4 and then square that value. Okay, so pi over 4 is a unit circle angle. So we can go to the unit circle. The secant is, of course, the reciprocal of the cosine. The cosine at pi over 4 is root 2 over 2. Okay, cosine at pi over 4 is root 2 over 2. So reciprocate that and then square it, and that goes in here. Okay, the whole entire thing. And that's basically times this value by 500, and you've got your dy dt. Okay, so this one comes from the unit circle. If the balloon rises at 100 feet per minute when the angle is 45, how fast is the angle changing? So now we know dy dt. So tan theta equals y over 500 becomes secant squared d theta dt equals 1 over 500 dy dt. Okay, so let's see, what do we know? Now we know this is 45 degrees. Okay, so we can once again use our unit circle to find that value. We know that dy dt is 100 now. Okay, changing at 100. So we can do some division and figure out what our d theta dt is. How fast is our angle changing? Okay, so a lot of these are done the same way, right? Especially when we have an angle and it's a tangent. Okay, whenever we have a tan, the derivative of tan is secant squared, and you go from there. Okay, volume of a cone problem. This one's really good. Water runs into the tank. So this is our change in volume, right? The water running in is the volume. The 10 and the 5 are telling you the relationship between the radius and the height. Okay, so eventually we're going to need to know this proportion. We compare the radius to the height at any given time, right? Any radius to height comparison. Since these are all similar triangles, okay, it looks like the radius is going to be half of the height. Okay, radius is half the height. But let's see what we need. How fast is the water level rising? So the water level is your height. So we're looking for dH dt when the water is 6 feet deep. So h is 6. Okay, so the volume formula for a cone is 1/3 pi radius squared times h. Now, because we want dH dt and you know the radius, okay, we're going to want to do some geometric substitution in order to replace our radius with a height. Okay, so just a second ago we said the radius was half of the height. So I'm going to replace radius with half of height and simplify this volume formula before I take its derivative. Okay, so I'm going to square all of my terms in here. This becomes a 1/4 h squared. Right, I'm going to be a little sloppy here. So this is now 1/4 times h squared when I square all my terms. Okay, now I do some simplification and I get the volume of this cone is pi times h to the 3rd power over 12. Okay, when I do my 3 here times my 4 there, that's my 12 on the bottom. And now I can take the derivative with respect to time. Okay, pi over 12 is a constant. The derivative of h cubed is 3h squared, and then I multiply it by dH dt. Okay, so I believe in my problem. I know what the volume is, right? The volume is 9. I know that the height is 6. So I can divide my volume by all this stuff, and that will tell me what the change in height is. Okay, the change in height. Okay, so that's how we do all these cone problems. We replace one variable with the other, implicitly derive, and then plug in the information we know. Okay, yes, this one is crazy. I 100% agree with you, but it actually turns out to be not too bad. Okay, so the x-coordinate is increasing, so that's dx dt. Just watch for a second. dx dt equals 6, and we want to know what dy dt is. Okay, and this is your x value, and that's your y value. Okay, so yes, this looks like a pretty complicated equation, but let's do some simplifying and cross multiply. Okay, are you okay with this? Let's cross multiply. So 5 times xy cubed plus x now equals 9 times 1 plus y squared. Okay, so no longer are there fractions here, so when we now implicitly derive, we don't have to worry about using the quotient rule. Okay, so implicit derivation. 5. This guy here, this is a product rule. Okay, this is your f value and this is your g value. So if we do f prime, that's 1 dx dt times y cubed plus f times the derivative of y cubed, which is 3y squared, dy dt, okay, and then plus the derivative of just x, which is dx dt, equals, right, over here on this side, this is 9. The derivative of 1 is 0, so that doesn't count, but 2y dy dt. Okay, so the derivative is actually really nice once you cross multiply. Okay, so we're going to do our substitution, right? We know some things here. We know that dx dt is 6, so we're going to plug in a 6 here. We know that y is 2, so we're going to plug in a 2 there. We know that x is 1, so we're plugging in a 1 here and a 2 here, right? And that's 2 squared times 3. We don't know dy dt, so that's our variable. Dx dt is again 6 over here, right? So there's a lot of things that we can do in order to simplify this, so it's not as scary. Okay, so we have a whole bunch of numbers. We have a couple of dy dt's, right? You're going to want to get them on the same side eventually, and you're going to want to get your numbers on the other side. Okay, so now it's just a matter of doing some algebra. All right, and now our last one. A spotlight is on the ground 21 feet away. So we know the whole entire distance is 21. And the man is 6 feet tall. Okay, those are constants. is walking towards the wall at a rate of 2 feet per second. So our distance from the wall is shrinking. So this distance is going to be x. Okay, and it's changing. dx dt is changing at -2 because you're getting closer to the wall, right? Your x distance is getting smaller, so that's going to be a negative. Let's see, how fast is the height of the shadow changing? So we're going to call this y, the vertical distance. We want dy dt when x equals 6. Okay, so we're going to set up a proportion because we have some similar triangles. Anytime we have this triangle inside of a triangle business, we have similar triangles. Okay, so we know that the wall is y, right? This is the shadow, and the whole entire distance from the shadow to the spotlight is 21. We know the man's height is 6. But what about this distance here? Okay, if the whole entire thing is 21 and this much is x, this must be 21 minus x. Yes, it's whatever is left after you subtract x from 21. So this is 21 minus x. So we have a proportion. We can write your proportion a couple ways. We can go y over 21 equals 6 over 21 minus x, or we can compare y over 6. Lots of ways to write our proportions. So let's do y over 21 equals 6 over 21 minus x. Okay, so now let's cross multiply and simplify as much as we can. So 21y minus xy equals 21 times 6 is 126. Okay, so now your job is to implicitly differentiate this formula. Okay, so let's look at this. 21y is 21 dy dt minus, okay, here's x times y. Once again, we have a product rule, right? This is f and this is g. So the derivative of x is dx dt times y plus x times dy dt equals 0 when we implicitly derive 126. Okay, so let's see, what do we know? We know that dx dt, right? We know dx dt. We know x. We know x is 6. Let's see, do we know y value? That's the question. Maybe we don't need to know. Well, let's do the, hang on a second. Hang on, let's go back for a second. Let me erase, sorry. Let me erase some of this. Let's go back up to here. Okay, since I want dy dt, let's go ahead and solve this equation up here for y before we do our differentiation. How about that? That sounds like a plan to me. I think that will work better. So both of these have a y in common, so let's factor out that y. 21 minus x equals 126. So y equals 126 over 21 minus x. Okay, that sounds like, okay, so now let's implicitly derive this formula with respect to time. So this becomes your dy dt, and over here we're going to use the quotient rule. Okay, watch, it's not so bad. Things cancel out. So low d high, 21 minus x times 0. The derivative of 126 is 0 minus high times the derivative of the low. So we have negative x is the only thing that has a derivative, and that's negative dx dt over 21 minus x squared. Okay, so our derivative with respect to time of the shadow is equal to 126 dx dt over 21 minus x squared. Okay, so those are all of your values. Now we know what dx dt is, right? We can plug in dx dt, that's -2. We know x equals 6. And after that, it's just a matter of simplifying down to its most simplified form. Okay, so hopefully this video has been helpful in helping you figure out how to do these tangent problems and then how to set up your ratios, okay, especially 24, right? Cross multiply, make sure there's no fractions. You could even distribute into here first, and then it's a matter of substituting and doing your best to simplify as much as you can. Okay, that's all.